All right, I think we're ready to go here now. All right, so section 3.5 is all about equation solving and doing a little bit of modeling. We're probably not going to get to the modeling part of that today, but we can talk about the equation solving. And the nice thing is, a lot of this equation solving you've already been doing. If you guys remember the last couple of questions we had from the homework, you were solving equations involving logs, right? So we're really going to be kind of doing that same thing. Just going to show you a couple different techniques that you could use that maybe would make some certain problems a little bit easier to try and solve. So we have these one-to-one properties that let us do that, and they should make a bit of sense here. So if you have, let's say, b to the u equals b to the v, what do you suppose you can conclude from that then? U and v have to be equal, right? So that's one of them. That's involving exponentials. Okay, so if you can get an exponential problem down to that, where both sides have the same base, then you can just say, oh, the exponential or the exponents are both the same. Similarly, if you have two logs that have the same base that are equal to each other, then it's essentially the same conclusion, right? Log base b of u equals log base b of v. So then the u and the v would have to be the same thing to make those two things equal. All right, so we're going to try this, see if we can solve some equations by hand doing this. So I'll start with an exponential example here. And sometimes it's going to take a little bit of manipulation to get it to look the way we want. Because right now, this looks nothing like this. And except for the fact that, oh, there's an x in the exponent up there, so it is exponential, so I can, recognize that. But beyond that, not much we can do. So the first goal that we have with this is to try and isolate the exponential part of it, okay? The exponential piece of this equation is that 1/2 to the x over 3. So what should I do then to isolate that by itself? Divide by 20, right. So if I divide each side of this by 20, five over 20 is 1/4. Okay, so now I'm a little closer. But I want to take this 1/4 now and write it in such a way that it is a base of 1/2. So 1/2 to what power gives you 1/4? 2, right? So this could be then 1/2 to the x over 3 equals 1/2 squared. And now it's like that one-to-one property we talked about. 1/2 to the x over 3 equals 1/2 squared. So we can go ahead and lose the bases. We know that this exponent needs to equal this exponent. So x over 3 equals 2. So what's the solution to that equation then? 6, right. Okay. Now, did I need to use that one-to-one property to solve that thing? No. And in fact, you kind of sort of did a logarithm in your head to set that thing up. So I'm going to show you an alternate way to solve it, just using logs like we've been doing, but you're going to see it's pretty much the same thing. You're just writing out log and all of that instead of just doing the log part in your head. So the first step is still the same. You still want to isolate the exponential piece of it. So I'm going to just copy down the same thing we did to start the last one. So 1/2 to the x over 3 equals 1/4. And probably in the past, this would be where you would then take this thing and turn it into a log equation, right? So it's log base 1/2 of 1/4 equals x over 3. Now, when you do a logarithm, like I've got a log right here, and if I could punch this in my calculator and get an answer, okay, and the answer is 2. But to do a log in your head, you really are asking yourself this question. What number do I need to raise this base to equal this thing? And didn't we do that before? I asked you 1/2 to what power is 1/4? 2, right? So when you look at a log, it's kind of a new way of thinking about this a little bit. When you are looking at trying to evaluate a log, that's what you're doing. You're taking what is this base, this to what power gives me that. And sometimes you can do it in your head like this one. I just raise it to the 2nd power and it works. Sometimes, the log comes out to some weird decimal or something and you can't do it in your head. But a lot of the time you can. So if you do that, okay, so that log needs to equal 2. So 2 equals x over 3. So x is equal to 6. Okay? For some people, just the visual of seeing 1/2 to this power equals 1/2 to this power and then reasoning it out, like this is much easier for them to digest. You don't have to write the word log. All right? You don't have to think about how do I compute a log again. Oh yeah, I got to do this to what power is that? Okay, or whatever. So it's just a different way to write it that might make it a little bit easier for some people. So I thought it was worth looking at. Let's do another one. This one will be with a log to start with, and see if we can use one of these one-to-one properties to do kind of the same thing. So let's say we've got log of x squared equals 2. Okay, so I've already isolated the log, which would be the first thing I'd need to do anyway. Okay, so that's already done. But if I'm going to use this one-to-one property that using the logs right here, I got to have a log of a base equals a log of a base, and the bases need to match so that I can use that. So I need to turn this 2 into a logarithm. So 2, if I have to keep this as a log base 10, because that's what this one is, 2 is log base 10 of what? 100, yeah. Okay, so think about that. 10 to what power equals 100? 2. Okay? So to get this number, you're basically doing 10 squared. The base to this number should give you that. So now that I have a log with the same base on either side, I can strip away the logs, and it's just x squared equals 100. And that's a little bit easier to solve. What is the solution then if x squared needs to equal 100? Yeah?
Could we write it in exponential form, and then you'd have 10 squared equals x squared.
You're stealing my thunder. Yeah, I'm going to do that later. You're right. You're absolutely right. But let's just finish this one right now. All right? So stick with the program, man. So what numbers will work for x squared equals 100? 10 and negative 10, right? Okay, so yes, do I have to use the one-to-one property to do this? No, I could just do what I've done in the past if that seems easier. So originally, yeah, so we've got this log equation. If we convert that into an exponential, that would be, well, let me rewrite the first problem again here, though. So log x squared equals 2. So if we're going to change that to an exponential, it's a base of 10 raised to what power? 2 equals x squared. And 10 squared is 100. And again, if 100 equals x squared, so then my solution would be x equals 10 and x equals negative 10. Okay, so in doing what we did over here, we basically did the same thing. To get this 100, what did we do? 10 squared, right? That's exactly what we did here to get this 100. So, yeah, you're kind of doing the same thing. I think, in general, this right-hand column's a little easier to digest with these, though, too. Okay, our brains like exponentials much better than logs for some reason. So if we write it out that way, that works, too. So I'm not going to tell you which way to do it. You're free to choose. Yeah?
Why bother with squaring the 10 when you can see what x is, since they both have the same exponent?
Why bother squaring the 10 when you can see?
Yeah.
Oh, because then you'd lose your negative 10.
No, you got plus or minus. You got 10.
Oh, because you have to do the plus or minus square root? I hear you, what you're saying. Yeah, you could do that, too. Yeah, that's fine. And then tomorrow we'll do the modeling side of things with this, okay?